when we're working in R2, we define the arc length of a parameterized curve as simply the integral from a to b, the square root of f prime of t quantity squared plus g prime of t quantity squared dt. And actually we will define the arc length of a space curve in really the exact same way. So given a space curve with a vector equation r of t, remember this is a vector, equals, it's parameterized as f of t, g of t, and h of t, so obviously we're in 3 space, where f prime, g prime, and h prime are all continuous, and the curve is traversed exactly once as t varies from a to b. This exactly once is kind of important. Then the arc length is then going to be given as L, arc length equals the integral from a to b, the square root of f prime of t squared from the x component, or the parameterization of x, plus g prime of t squared, here's the y component, plus h prime of t squared dt. Now that is actually equal to, it's the same thing as going from a to b, of the square root of dx dt squared plus dy dt squared plus dz dt squared dt. Now, something I want you to note here, hope you notice, now when we're thinking in terms of this parameterized vector r of t, note that the magnitude of r of t, think about that. What do we do to calculate the magnitude of the vector? Well, that is equal to the square root of f prime of t squared plus g prime of t squared plus h prime of t squared. So actually we can represent the arc length as simply L equals the integral from a to b of the magnitude of the vector function, the derivative of the vector function of t dt. And actually I had one typo right here. I need, there. The magnitude of the derivative function would be this. The magnitude of the original function would simply be f prime squared, g prime squared, h prime squared. But the derivative, the magnitude of the derivative function would be these quantities squared, because these are all first derivatives. So what this is really doing is this is simply a very compact way to write the integral. So let's take a look at a quick example here. Let's find the length of the vector function r of t equals cosine t, sine t, ln of cosine t. And specifically, I'm going to be interested for t from 0 to pi over 4. So the arc length, L, is going to be equal to the integral from 0 to pi over 4 of the square root of the derivative of cosine, which is negative sine, of t squared, plus the derivative of sine, which is going to be cosine squared of t, plus The derivative of log, well, derivative of log of cosine is 1 over cosine times the derivative of cosine, which is negative sine over cosine. That's simply going to be negative tangent of t quantity squared dt. Well, this is just going to be sine squared and cosine squared, so that's sine squared plus cosine squared is 1. So this is going to equal the integral from 0 to pi over 4, or the square root of 1 plus negative tangent squared is just tangent squared dt. Well, 1 plus tangent squared, that's secant squared. So this is actually the square root of secant squared. Well, square root of secant squared is just going to be secant. So this is really nothing more than the integral from 0 to pi over 4 secant t dt. Now, one thing I would be careful of is this is a square root of secant squared, so it's always going to be positive, but secant is actually positive from 0 to pi over 4, so we don't have any issues there with it being negative and dealing with a radical. So I will put this in here because, you know, technically that should be there. If it's not that big of a deal, it's really the same as secant here. Now, this is actually going to be equal to, if you remember the antiderivative of secant, that's going to be log of the absolute value of secant of t plus tangent t. And of course, I need to evaluate this from 0 to pi over 4. Well, that is going to be equal to the natural log absolute value of secant of pi over 4 plus tangent of pi over 4 minus the natural log of secant of 0 plus tangent of 0. Well, secant of pi over 4 is, well, I'm going to go ahead and write all this out. I'm going to go skip these steps for you right now. Remember, secant is 1 over cosine, so this would actually be 1 over the square root of 2 over 2, which clearly you can see we're going to simplify that. Tangent of pi over 4, well, that's going to be 1. Minus ln secant of 0 is 1. Tangent of 0 is 0. So this component over here is actually 0, because this is ln of 1, which is 0. So we're going to end up with ln of, well, when we simplify this, you're going to get square root of 2 plus 1. So that's the solution, which is obviously positive, so we could drop these absolute values if we wanted to. This is just ln of 1 plus root 2. That's the exact value, and of course you can grab a calculator and go ahead and estimate it if you want.